Imagine, if you will, two explorers, separated by the vast silent darkness of space. One stands on the red soil of Mars, and the other on a moon orbiting Jupiter, light years away from any star we know. Before they left, they shared a single peculiar object, a coin, let's say, which they carefully split into two halves. They each take one half, place it in a box without looking, and blast off to their distant destinations. Now, adrift in the cosmos, the Martian explorer opens her box. She sees her half of the coin has landed heads up. At that very instant, she knows, with absolute certainty, that her partner's half, light hours away near Jupiter, has landed tails up. It's not a guess, it's a fact. This isn't magic, it's a whisper of a deeper reality, a fundamental connection that really just defies our everyday intuition about how the universe should work. This puzzle, this cosmic ghost story, baffled even the greatest minds of the 20th century, including Albert Einstein himself. He called it spooky action at a distance, a phrase that perfectly captures the unsettling, almost supernatural quality of this phenomenon. Let's journey down to the scale of the unimaginably small, the quantum realm. Here, particles like electrons and photons don't always have definite properties until we measure them. Think of an electron's spin. Before you look, it isn't spinning up or down. Instead, it exists in a blur of possibilities, a state of both up and down at the same time. It's only when you make a measurement, when you force it to choose, that it settles into one definite state. Now imagine you create two of these electrons in a special way, so that their fates are intertwined. They are now an entangled pair. If you set them up so their total spin must be zero, then if one is measured to be spin up, the other, no matter where it is, must instantly become spin down. The idea of an instantaneous connection across the galaxy immediately sparks a thrilling thought. Faster than light communication. Could we use entanglement to have a real-time conversation with a colony on Proxima Centauri b? Imagine picking up a phone and getting an instant reply from someone 4.2 light-years away, bypassing the long, frustrating delay that light-speed communication would require. Here's why. While your measurement on your particle instantly affects its partner, you have no control over the outcome of your measurement. The result is completely random. Every time you measure, it's a 50-50 chance of getting up or down. Your friend on Mars doesn't know you've even made the measurement. All they see is their own particle, which, when they measure it, also gives a random result. And how do you tell them? You have to use a conventional communication method like a radio signal, which travels at, you guessed it, the speed of light. If entanglement can't send messages faster than light, then what is it good for? Its true power isn't in speed, but in something equally vital for an advanced civilization: security. Entanglement provides a way to create a secret key, a shared piece of information known only to the sender and receiver that is protected by the very laws of physics. This method is called quantum key distribution, or QKD. What if a spy, let's call her Eve, tries to intercept the entangled particles and measure them to learn the key? The moment she measures a particle, she disturbs it. When Alice and Bob later compare a small sample of their key, they will find mismatches and errors that shouldn't be there. The presence of these errors is a dead giveaway that someone has been listening in. This method doesn't rely on complex math problems that a powerful computer might one day solve. It relies on the fundamental nature of reality. It's a security system guaranteed by the cosmos itself. The concept of entanglement can feel abstract and hard to grasp. So let's try a more down-to-earth analogy. Imagine you have a special machine that always produces a pair of socks, one red and one blue, but it places them into two separate, identical boxes without you knowing which is which. You keep one box and you ship the other one to your friend on a distant exoplanet. But the moment you open your box and see a red sock, you know something with absolute, instantaneous certainty. You know that your friend, light years away, has the blue sock. Now let's extend this analogy to see why it isn't faster than light communication. You couldn't use this system to send a message. You can't decide to find a red sock in your box to tell your friend the number one. The color you find is completely random. The information only becomes meaningful when you later call them on a light-speed telephone and say, "Hey, I got the red one." Then they can confirm, "That makes sense, I got the blue one." The promise of a perfectly secure, galaxy-spanning communication network is one of the grandest visions in science. We have already demonstrated it on Earth, sending entangled photons through the air and via satellite over hundreds of miles. But the cosmos is vast, and the challenges of scaling this technology up to interstellar distances are immense. Our galaxy, the Milky Way, is about 100,000 light-years across. To make interstellar quantum communication a reality, we would need to build a network of relays, a series of quantum repeaters stationed in deep space. Each repeater would catch an incoming entangled particle, perform a special operation called entanglement swapping to transfer the entanglement to a fresh particle, and then send that new particle on to the next station. Building this infrastructure would be the most ambitious engineering project in human history. It would require launching and maintaining a fleet of highly advanced autonomous satellites positioned with incredible precision across interstellar space. The journey from a curious, spooky action in a laboratory to a secure communications network spanning the stars is a long one, but it is a journey powered by the deepest human impulse: to explore and to connect. Think of the future this technology could unlock. It would allow future colonies on distant worlds to be part of a single, unified human civilization, sharing knowledge, culture, and governance without fear of interception. It is the infrastructure of a true galactic federation, built not on fleets of starships but on the subtle and powerful laws of quantum mechanics. One day, our descendants may look up at the night sky, not as a collection of distant, isolated points of light, but as nodes in a vast, interconnected web of communication. They will send their thoughts and secrets across that web, woven from the ghostly threads of entanglement, secure in the knowledge that their conversations are for their recipients alone. We stand today on the shore of that new cosmic sea, with the knowledge and the ambition to begin weaving the first threads. The age of quantum exploration has begun. Don't forget to subscribe to the channel for more interesting content.